Thanks everyone for this joining this webinar. So this is the fourth webinar of our webinar series on telco network strategy, telco architecture, and on evolution. I'm like towards the evolution of 5G. So in this webinar, we will cover some introduction into 5G radio access network and also into core network and how that evolution would happen. And we have covered most of the radio network stuff and also core network stuff in previous webinars as well, but we will deep dive into some of the technical details in this webinar itself. So th this is the sort of agenda of this webinar. We will do sort of a 5G new radio introduction. I mean, like in the radio AI interface and also Node B evolution. And then we will go through NR protocol stack and the functionality of each and every protocol or layers of NR protocol stack and frame structure and interface characteristics. And then we will go through 5G radio panel architecture and how it differs from 4G LTE. And then we will go through control and user plane enhancement to a certain extent. And then what is happening with 3GPP releases and all that. We will cover front hall architecture uh, briefly, since we have covered that in transport network architecture webinar. And then we will go through RAN evolution and the architecture as well. And I mean, like OpenRAN evolution and architecture. Then service-based architecture related to 5G core and different deployment architectures, and then NR core slicing. NR and core slicing, something that we have covered in previous webinar, but we will go through that one in brief in this webinar as well. So if you take 5G as a standard, I mean, like in previous webinars, we covered that 5G is a 3GPP specification. So it's defined by an organization called Third Generation Partnership Project. So under that 5G, I mean, like 5G has, I mean, like 3GPP has already released uh, pre-releases already. That means release 15 that was released back in 2000, end of 2018 and early 2019 timeframe, and then release 16, and then release 17, very recently released last year, uh, Q2, and then we're about to see release 18 maybe by end of this year or early next year. Uh, So those are the releases, and I will go through some of those technical details. And we have covered the 5G new radio in briefly in the previous webinar, so we will not go into the uh, do some sort of a very, I mean, like introduction into NR and all that, but we will go through the technical detail uh, in this webinar. Okay, so if you take 5G, there are a lot of differences in mainly in the frequency spectrum used, and there are three main frequency spectrums, I mean, three main frequency bands defined in by 3GPP. First one is FR1, which means from 410 megahertz to 7 gigs range. So this is the frequency band that we mainly use for 5G new radio applications. And then we also can use FR2 band, and so that means from 24 gigahertz to 52 gigahertz, that range. And then very recently in the latest 5G release 17, they also included this 52 and upward band as well, that is FR22. So those are the main frequency bands that we will use in 5G new radio. And if you look at each releases and how those releases differ from each other. So in the first release that was released back in release 15, we had the introduction of, I mean, like release, I mean, like introduction of service-based architecture. So that means it's a design approach where network functions expose their services through APIs and enable flexibility and easy integration with other network functions. So we will go through that one as well, since we have already covered that one. And and the other part is end-to-end network slicing was also introduced in 5G release 15 itself, so it was also there, and then some QoS announcements and network capability exposure, network functions like network exposure functions and all that stuff, and then location service related information. I mean, provide more accurate and reliable positioning information for various applications and services. We will cover how that would be done in 5G core itself in the upcoming slides, and then support for non-3GPP access mediums. That means Wi-Fi and some other mediums as well. So in the release 16, they focused on mainly came up with new specifications for cellular IoT and then industrial IoT. That means 5G LAN, a non-public network, time-sensitive networking, and all those things as well. And then the URLLC requirement specifications were also defined in release 16. And then network automation and analytics related uh, specs came in release 16 itself. And then wired and wireline convergence, something that you may have heard already, or maybe that means WWC. That means you should be able to converge wired core with the 3GPP core. So those some specifications related to that also came in release 16. And then ATSS, that means access traffic steering, switching, and splitting uh, techniques. So there were a lot of specification related to that one as well. Then UE capability signaling optimization. That means optimization of user equipment capability signaling and to reduce the overhead and improve network performance. So those things came in release 16. And in release 17, we started seeing certain specifications related to enhancement for edge computing, and then also industrial IoT, and that means TSN and NPN phase 2. And also we started seeing phase 2 development of network automation related specs for uh, in 3GPP in the phase 2 itself. And so those were the things, and also 5G D2D proximity services. That means device-to-device communication and proximity services in 5G networks. That means allowing communications directly between uh, devices without going through the base station. So those specifications came in release 17 itself, and then also some improvements for 5G multicast and broadcast services. So there were a lot of specifications and some specification related to that one as well. And apart from that, very important uh, improvement that was I mean, like using non-terrestrial networks. That means low Earth orbit satellites for 5G radio transmission and also for backhauling. So the specifications related to that one also came in. NTN related specs came in the release 17 itself. So the release 18 is the new uh, specification that is about to be released in, I mean, like next year. So that means the studies and also specification efforts are already ongoing. So we will be able to see new improvements related to some AI ML related improvements in the AI interface itself, and then CSI feedback enhancements, the management and positioning accuracy related enhancements, and then in our side link and all those things we will be able to see with release 18, and also especially new radio red cap. That means uh, usually for maybe IoT kind of scenarios, I mean, like reduced uh, energy applications in radio equipment. So those will be there in the upcoming release 18. Uh, so what I meant by red cap previously was that that means mainly something that we can use in uh, non-3GPP, I mean, like non-mobile devices, and and to give higher performance, but with lower energy consumption, and should be able to have infinite or long-term battery life, and to save energy costs and all those things. So that should be I mean, like capable of delivering that with red cap specifications or red cap devices. So those are the things mainly related to those 3GPP specification and what has been going on in the industry itself. And if you look at the 5G adoption worldwide, I mean, in Sri Lanka, we have not yet deployed 5G commercially. Still, a lot of trials are ongoing with multiple operators. Uh, and But overall, if you look at worldwide, and the 5G deployment is still ongoing, and we have not yet reached 5.5G deployments, because we have not yet come to 5.5G. That means LTE advanced. That means after release 18. So if you look at sorry, if you take 5G, there are two means of deployment. One is standalone, and the other one is non-standalone. That means you'll be connecting your radio network directly to your 5G core, or maybe you would be connecting your 5G radio to LTE core. That means 4G core. So those are the main options that we have. So here you can see the worldwide number of LTE deployments, and then the 5G deployments on the other side. So if you take as a whole, there are on 259 deployments worldwide, and mostly non-standalone deployments, and most of those deployments have happened in uh, Europe. And if you look at the standalone deployment numbers, then it's relatively low. And so you can see in this graph itself that there are around 37 standalone deployments itself. I mean, alone, and more than 96 countries have already deployed 5G commercially. So we will deep dive into 5G new radio, and very important aspect when we study 5G RAN interface is to know about the 5G new radio frame structure. So if you look at, or if you're already familiar with the LTE itself, then in LTE we also used to use uh, orthogonal frequency division multiplexing to as an access technique to carry information back and forth, use equipment, and also back and forth use equipment, and the node B in 5G new radio. So we are not seeing a big difference. We are seeing some differences. We are using frequency domain, and we are also using a time domain. So, but we have introduced some new terminology called numerology. I mean, in 4G we used to use different. I mean, like if you take some sort of a frequency band, we take let's say 10 megahertz band or something like that. In OFDMA, what we do is we would uh, take the entire frequency band and split it into small subcarriers, and the entire frequency band will consist of different subcarriers of 15 kilohertz subcarrier spacing, and they are orthogonal to each other. So that's why we use the term orthogonal frequency division multiple access. Then at the same time we would use time domain, and so this atomic unit, that means a smaller unit of, so sort of a, I mean, in the AI interface itself is it's a resource element. So each resource element could comprise of multiple symbols. Technically, it would be around 14 symbols in 5G new radio. In LTE, it could be around 7 symbols. So symbols means that the number of, I mean, like, so each resource element, that means it could be based on the modulation technique that you use and all that stuff. So in 5G, we introduced a new uh, term called numerology. That means numerology can uh, that means it can, I mean, like, based on numerology is sort of a number that they define. So based on the numerology, let's say if it is 15 kilohertz, then it's numerology 0. And then if you go into higher numerologies, that means let's say numerology 1, 2, 3, 4, like that, then the formula is 2 to the power mu minus 1. That means you will uh, have higher subcarrier frequency spacing. That means, let's say you are in numerology 1, that means the subcarrier spacing between two uh, frequency subcarriers adjacent to each other would be 30 kilohertz. So if you go into higher numerologies, that means that would increase. So that's what is represented over here. So numerology is represented by the term mu. So each slot will contain 14 symbols based on the modulation technique that you would use. And so those are the building blocks of a 5G radio frame. And each radio frame would consist of a 10 millisecond time interval. So 10 millisecond time interval can be considered as a radio frame. So we can split that into radio subframes of 1 millisecond, and each subframe could contain 14 radios, like OFDM symbols. And based on the numerology, let's say if you're going for higher numerology, the number of slots that you can encapsulate inside a subframe would increase. That means uh, the time difference between two symbols would be very short. So because of that, you get better latency, because the amount of time that it takes to carry information back and forth in the AI interface itself would reduce. So that means you can improve the latency. So let's take 5G itself. Then in 5G, if you have some lower latency applications, then you can cater that based on the numerology that you would select. So uh, and the other thing that I want to highlight is that we use the term resource grid to represent. Like we can use the term resource block to represent 12 subcarriers, and then we have not defined the time domain, so 12 subcarriers, and the entire thing can be considered as a resource grid, and that's it. And in the next upcoming slides, we will go through the other structures as well. So the other very important aspect that we need to understand is 5G new radio control and user plane protocol stack. So it does not differ from LTE. Like there's no big difference from LTE protocol stack, but the functionality is different. So mainly there are a few layers. One layer is, which is familiar. You may be already familiar if you have worked with LTE. Then one is PDCP, protocol data convergence protocol, packet data convergence protocol, and the radio link control. Then MAC layer and PHY layer. And in 5G, there's a uh, new protocol called SDAP, introduced for QoS management and all those functions. So we will go through the stuff in detail in the upcoming slides. So there are two stacks predominantly. One is for user plane and the other one is for control plane. So what differs from each other is the upper layer protocols, that means SDAP, and then and also RRC and mouse layer for control plane signaling between the user equipment and also the radio G node B. So you will have to have some sort of an RRC connection that would do UE capabilities and other control plane configuration message between user equipment and G node B, and then you can have non-access stratum similar to LTE between the user equipment and the AMF itself. So uh, this is the basic protocol structure of 5G new radio, and each uh, payload. Let's say you want to transmit something like some web surfing traffic or some sort of a web traffic or whatever. So let's imagine that you would have certain IP packets, and then each IP packet could be considered as a service data units for the layers below that. So we use the term SDU for that. And so this is the structure that you would translate those different IP packets into those radio uh, uh, radio equipment protocol stack. That means of the G node B and the user equipment itself. And we also have introduced a new protocol called next generation application protocol, mainly used for the communication between G node B and the access and mobility function, mobility management function in 5G core. So that's the new improvement. And Then we will go through them in detail in the upcoming slides. So if you look at service data adaptation protocol, if you predominantly take the 5G user plane, uh, the step layer only exists in the user plane, and it interface with upper layers with via QoS flows, and then PDCP lower layer via radio bearers. We usually call data radio bearers, and traffic from different QoS flows are mapped to suitable DRBs through that step layer, and the main uh, service provided by step to upper layer is the transfer of user plane data. That's something that you have to keep in mind carefully. And the other thing is usually a step expects uh, in sequence delivery of different PDUs from the layers below. So the main function of a step in summary uh, is QoS management and mapping those different IP flows, and tagging them with QoS uh, tags, uh, and then mapping into the lower layers and vice versa, and also controlling in sequence delivery. And PDCP is not a new layer; it was there in LT itself, but there are few improvements to PDCP itself. So it's a layer that lies between RRC and RLC, RRC and RLC, or maybe a step and RLC layers. So PDP provide services to upper layers as RRC and a step, and the main function of PDCP is header compression and decompression, and using compression mechanism called robust header compression, ROHC, and also deciphering and deciphering user plane and control plane data, and also doing integrity protection and verification, and things like that. And the other uh, main important layer is the RLC, that means radio link control. So it interfaces with PDCP layer and also the MAC layer. I mean, mainly via logical channels. We will go through them in detail in the upcoming slides. So there is one-to-one mapping between RLC SDUs belonging to an RLC channel, and they also map to a single logical channel. And and the other thing is RLC can be configured in three transmission modes, very important. That means one is called unacknowledged mode, and the other one is acknowledged mode, and another one is transparent mode, usually based on the kind of session that you have between user side and also somewhere in the internet or somewhere. Then you can choose which mode that you will select, whether you want reliable transmission, then you will go with acknowledged mode, or it's a TCP transmission or whatever. Then if it is not, then you can select the unacknowledged mode, so that will decrease the number of messages that will flow between. And the other most important layer is medium access control layer, that means MAC layer. And what it does is it maps information between logical and transport channels, and we will explain them in later. And then this MAC sublayer can provide two main services to upper layers. That it means data transfer and radio resource allocation, and also it can support hybrid ARQ mechanisms, and that means ARQ means automatic repeat request. That means providing reliability in the MAC layer itself. We can also do that in the upper layers as well, and also doing some logical channel prioritization. And this is how the channel mapping looks like in 5G radio. And because in 5G and also in LTE, channels play a very important role, and channels can be categorized mainly into three main types: logical and physical, and also transport. And so here you can see different types of channel. I will go through them one by one. So one is broadcast control channel. You can see over here or over here. So that means what BCCH does is that would broadcast mainly system related information. And then there's a channel called paging control channel that would do paging. That means let's say if a user equipment is connected or not, then doing that paging procedures will happen through this PCC channel. The PCC channel in the logical layer will map to down, I mean like layers down below. That means in the transport layer and in the file layer. And uh, the main function of CCCH is transmitting mainly control information between user equipment and the network when users have mainly no RRC connection with the network. And so and the other channel is DCCH. It's also a point-to-point bidirectional channel that we usually use to transmit UE specific control information between user equipment and network. And it is mainly used by UEs that have established RRC connections with the network. So and the other thing is uh, and other important thing is that you have to understand the mapping that happens between different channels. So for an example, if you take BCCH, that can be mapped to broadcast control channel down below. And and uh, this is something which can be characterized by fixed or predefined transport format, and it is mainly required to be broadcast in the entire coverage area of the cell. And DLSCH over here also may support receptions using different numerologies and TTI's duration. Durations within the MAC entity, and it's also there. And I will not try to go through each and every channel over here, but the main idea you have to understand is that there are multiple uh, protocols in the AI interface itself, but they also map into those different channels, those abstractions that are defined, and that can be used to carry different types of information with different types of QoS levels and different types of control mechanisms and scheduling mechanisms. And so those are the capabilities that you will predominantly get with uh, those channel kind of mechanisms, right? And the other very important layer in 5G radio is the PHY layer, because in the previous slides we talked about those layers. That means we can use the term L2 layers in 5G radio, and the L1 layer. Uh, we did not talk about this one, but this L1 layer is one of the most important layers, because that would do the conversion between upper layer uh, digital components into the RF processing and all that stuff. And so there are multiple layers to that one as well. That means we will take different transport blocks or different types of uh, message blocks. And then what we will do is we will send those different transport blocks through different types of, let's say, functional blocks to do, let's say, CRC or cyclic redundancy checking, and to do LDPC. So usually what LDPC does is, uh, I mean, like if you take LDPC itself, LDPC is mainly used in different types of communication systems, and also in wireless communication systems. It's not related to only related to 5G radio. And usually what they do is like they perform iterative message passing algorithms like belief propagation, and also some product algorithms. And there are a lot of technical details related to that stuff. So I will not go through them, but uh, so we will go through different types of blocks when we do 5G radio file layer processing. And and over here. So what happens at the end is that we will take all those LDPC encodings and then bit scrambling and all those things, and we will do modulation, and also we will do layer mapping. That means if there's some sort of MIMO configuration, so we will uh, send that information into different radio antenna elements. So the file layer itself is very important, because based on the file layer functional blocks, we will define how we would split the 5G radio uh, processing between different types of elements in the radio access network itself. So let's say if you want to build a 5G front haul, then some front haul functions will happen. Let's say you want to carry some radio unit processing or RE processing to a certain component, then that split will happen between those different blocks in the 5G file layer itself. Okay. And the other important aspect in radio access network is, I mean, like in the previous webinar, we talked about 5G network slicing. So in the radio access network itself, then there are things that we can do to support slicing. That means to provide multiple virtual networks in the AI interface itself. And one way that we can do slicing in the radio access network is I mean, like using different types of numerologies and different types of subcarrier spacings and all that. And then we can also do slicing using beamforming. That means beamforming is an advanced antenna technology that mainly focus on radio signal energy in a specific direction, and to improve the signal quality and then throughput. And so based on the phase of the signal, we can, I mean, like if you change the phase of the signal, then we can change the direction of the azimuth or horizontal plane of the signal. So we can do things like that. And the other way we can do schedule, I mean, like slicing in the 5G radio itself is using a different type of RAN protocol scheduling. And based on, let's say, it could be based on a file layer, or it could be based on the MAC layer, and how we would schedule different types of streams uh, down below. And the other important part is we can use something called the bandwidth part. That means bandwidth part is a construct defined in radio transmission. That means you can use some chunk of frequencies or subcarriers to allocate certain resources, certain user resources in the radio interface itself. That means in frequency domain and timing domain. And the other thing is MIMO. And so MIMO is an antenna technology usually used for, I mean, like used at both at transmitter and the receiver to increase the capacity and also reliability of wireless communication systems. So in the context of network slicing, the MIMO can be used to optimize the performance of individual slicers based on their specific requirements. And also in 5G radio, we can make use of different types of radio bearers and to allocate certain resources to different network slicers. So there are a lot of constructing 5G RAN slicing itself. When you want to do slicing, one is scheduling. You can use bandwidth parts, you can use numerology, you can use beamforming, you can use a lot of things. And also you can use different types of CU and DU user planes, uh, CU user planes, and also control plane. Uh, I mean, allocations based on the slicing requirements. So there are a lot of technical details related to that. So I will not be able to go through all of them in this presentation, but later we will try to cover them. And so this is how 5G radio uh, front haul would look like. So I mean, I talked about this, that you can bring different types of file layer functions. In the previous slide, I mentioned different, I mean, we can split different types of file layer functions, and we can bring those file layer functions into different network segments, that means radio units and DUs and CUs. So between radio unit and DU, we have something called front haul that we have covered in last webinars themselves. That means uh, so that means you can carry lower PHY processing and RF PHY processing at the radio unit itself. And also you can decide what kind of functional blocks in the PHY layer itself should happen at upper PHY layer and lower PHY layer. So based on that, the vendor support will also differ. So some vendor radio units might not support vendor units from another vendor's DU because of the way that you split the PHY layer functions, like how you would do LDPC coding, how you would do CRC, how you would do scheduling and all those things. So where you would split all that would define what kind of functionality that you will have and what kind of interoperability that you will have between radio units and distributed units. So there has been a lot of uh, efforts, I mean, to open up those interfaces, and that's why I mean, like I covered OpenRAN in last previous webinars as well. So they have already defined different types of specifications for 5G front haul, and and where that split should happen, and what kind of message flows that they need to have, control messages and control management planes and all those things. So they are defined in OpenRAN. So that effort is already ongoing. And one of the most important aspect that we need to understand in 5G itself is the deployment options, because in the first slide I mentioned that most of the deployments worldwide related to 5G are deployed in non-standalone, and standalone deployments are already going on. But the thing is, when you deploy 5G network in non-standalone mode, then that means that you'll be connecting 5G 5G radio into a evolved packet core, that means LTE core. So there are multiple options to do that. I will skip this slide, and so you can see over here that there are multiple options defined by 3GPP. So the first option is this is sort of a baseline for other deployment options. Option one is that you would be connecting LTE radio to an evolved packet core, like the previous generation. That's the previous generation. That means you have LTE PC, then you have LTE radio. Then option two is that you'll be connecting 5G new radio to 5G core. That means this is full standalone. So this is defined by 3GPP. So this is the standalone mode. And then the other option is option three. So option three has three other options, option 3A and option 3X. We will go through them on the next slide. And the option four is that would be connecting LTE radio uh, and 5G new radio to 5G core, that which is called NEDC, and the previous one was called ENDC, ultra new radio dual connectivity. And the other one is option five. Uh, Option five, so that where you would connect LTE radio directly to a 5G core, and option six is not mentioned over here, but it's a hypothetical deployment where you would be connecting 5G radio to evolved packet core directly. So that kind of deployment. So this is not properly defined or standardized in 3GPP. Then option seven, where you would have LTE radio, 5G radio, evolved packet core, and 5G core, and with two core networks. So those are the options that you have. And the most popular option is using option three to connect uh, LTE 5, 5G radio to evolved packet core, that means LTE core. And I will go back to the previous slide. So this is the option. This is how we would connect. And there's very important terminology that you want to understand. So we would use the term master node and also secondary node, where master node is where you would terminate your control plane signaling, and the secondary node would be the other one. Okay. So based on the master node and secondary node, this terminology, then there are different types of split bearers defined. And so I will not go into very detail because there are a lot of technical details that you want to know about the primary cells, secondary cells, and MCG split bearers and all those things. So I don't have time to cover all that. But the idea here is that you'll be connecting, you will not be to G node B. I mean, like E node B will take care of control plane signaling with the user equipment. So that will establish control plane signaling, and then you can split data plane or data bearers with the G and B and E node Bs, and the G node B itself can be connected to another E node B. So you can have some sort of data plane connection. And in the option 3A, you don't need to carry control plane information, sorry, user plane information between the E node B and the G node B. You can directly connect G node B data plane to the evolve packet core, and also vice the same way the E node bits as well. And in the option 3X, so you can connect uh, data plane with both E node B and G node B. At the same time, you can have ENB, GNB in between connectivity in the data plane or XN interface itself. So this should be corrected as X. Oh, sorry, this could be X2 or X2 interface itself. And so those are the deployment options. So most popular is only 3X among operators. And most of the operators are going in this direction. The main reason is it's easier to do upfront, because instead of investing in 5G packet core from the very beginning, 5G core from the beginning, it's easier to build the radio access network first and then migrate your to 5G core. But there are disadvantages as well, because you will have to go through two steps. That means you'll have to at some point in time, you'll have to invest on 5G core itself. So there has to be some sort of a migration effort that you will have to take into consideration. And previously we talked about OpenRAN. So this is a slide that I have taken from previous webinar itself. And so OpenRAN is gaining a lot of popularity because we're trying to open up interfaces between radio units and distributed units and those central units. I mean, like splitting up them, and also trying to bring openness in between different types of interfaces that you have. At the same time, bring virtualization to the edge. And OpenRAN itself has an architecture very clearly defined, or an architecture where you have radio controllers on top of that. So we have gone through this one in the last slide, so I will not try to go into uh, very details. And so the other part is 5G core. So it's very important to understand how 5G core differ from LTE packet core or LTE evolved packet core. So the main difference in 5G is that 5G is based on service-based architecture. So it's a fundamental shift in the design of mobile network core components, and that means moving from traditional node-centric approach to a flexible, modular, and also service-oriented architecture. So the SPA allows network functions to be exposed as services, enabling better scalability, more efficient resource utilization, and also simpler network management. So that means you'll be exposing those different 5G core network functions as microservices. So we can take, let's say, some sort of a container network functions, a bunch of container network functions being exposed as some sort of a microservice. In the sense of, let's say, if you take Kubernetes, and then how you would expose a service. So the same principles apply into the 5G core itself. So from the very beginning, 5G core is expected to be cloud native. So those network functions would be deployed as uh, cloud native network functions. And the other thing is each and every network function should expose application programming interfaces. So they could be mainly based on REST APIs and JSON as the object notation, and then based on transport protocols like HTTP2 or maybe HTTP3. So I mean, in the future. So those are the things related to 5G core evolution. I mean, like if you take the uh, early, let's say, evolved packet core. So evolved packet core did not have some architecture like that you'll be exposing different types of services and through HTTP RESTful APIs. So you used to have some protocols like diameter and different kinds of uh, very strictly defined interfaces, point-to-point interfaces. So 5G core is in that sense very different and very agile, and core network functions and how those things should come together. Uh, So this is a very detailed representation of a 5G core, and also some network function that would be necessary to do wired and convergence. So one network function, I mean, I have covered this one briefly in the previous webinar itself. So one very important part in 5G core itself is the access and mobility network function, which is sort of similar to mobility management entity without the session management. And so what AMF does is it does mobility management and like location tracking and handle security aspect of the core network and authentication and authorization. And also it interface with AUSF, that means authentication and service function. And there's the other very important network management function is SMF, session management function. So SMF is responsible for managing user equipment sessions and establishing and maintaining and releasing data connections between user equipment and the data network. And it also handles IP address allocation, very important, and also manage traffic routing and working with user plane functions. That means it works with work with user plane function and forward data packets between UEs and also uh, external functions. So it acts as the control plane for the UPF. And user plane function, as its name implies itself, uh, so what it does is it forwards data between user equipment and the external networks, such as internet. And it also does packet routing, QoS enforcement, and mm, charging data collection. And also UPF can be deployed in various locations in the network itself. It could be deployed at the edge site as well. And other network function is AUSF, authentication server function. So it's also responsible for authentication and authorization of user, uh, s- over here, authentication and authorization of the user equipment in the 5G network. So it works very closely with AMF and also with UDM, Unified Data Management, to verify user credentials and ensure secure access to the network. And other very important network node is UDM. So it's similar to HSS in uh, for GLTE. So UDM is responsible for subscriber data, including subscriber profiles, authentication, credentials, and access policies. So it provides centralized repository for subscriber data, and which can be accessed uh, by network functions such as AMF and AUSF. So those are some of those network functions. Uh, in the 5G network. So there are like PCF, policy and charging functions, network site selection functions. So I will not go through all of them one by one, but they have a lot of similar functionalities. I mean, different types of functionalities. And so this is how things would look like, and how we would deploy this kind of network architecture would be based on different types of cloud native environment, and where you would have, let's say, uh, based on, let's say, some sort of a container, set of containers, as I explained in the previous slide. Then we can deploy some sort of a service mesh between different core nodes as well. And then we might need to have some sort of a cluster management software on top of that. So those are the changes that we will see uh, in the 5G core network itself. So we have come to the end of this webinar. Uh, so presentation. So if you have any questions, and you can ask me.